Hi, everybody. That's the second lecture for Fourier series. And we're going to explain today how to express any periodic signal into Fourier series using trigonometric Fourier series. In this slide to the left, you can see the expression for this Fourier series, x of t. It's the periodic signal, and it can be expressed as a series of these components. The first component in note is the DC component. And the second component has two parts, sine and cosine terms. The cosine terms has coefficient equal AK. The sine term has coefficient BK. The coefficients of the trigonometric Fourier series A naught, AK, BK, their values can be found using these three integrals. That's the first A naught for the DC component, and that's AK, the coefficient for the cosine term, and that's BK, the coefficient of the sine term. And all of them depend on integration over the period t. So what's t? T is the period of the signal x of t. Let's just apply these equations to one example. The first example we're going to explain, train or rectangular train of pulses, and the first thing we should find the period of the signal. You observe that this signal starts from t equals 0 at 1 and then go down 0, 0, and then go back up again to 1, up to here. It's done 1 period, and then it's going to be repeated again. So the period of this signal starts from t equals 0 up to t equals 2. So the period is equal to second. You can write t is equal to second. When you do the integration should cover one period. So you have to choose. Actually, you have many choices. Maybe somebody will say, I'm going to integrate from 0 to 2. That's right. Somebody say, I'm going to integrate from -1 to 1, because it will be equal to the period in this time. That's also fine. Actually, I'm going to use the second choice. I'm going to integrate from -1 to 1 for this period. So let's go ahead and use the tablet for solving the example. Okay, that's here. I cut just one period where I'm going to do the calculation for the coefficient. Well, let me write first the coefficient A naught, the DC component. It's equal to 1 over t, the integration over the period t, x of t dt. In this example, the period is equal to 2. Just let me remind you, t is equal to 2 seconds. And integration from -1 to 1. And you have 1. That's the value of x of t. But not everywhere. It's only 1 from -0.5 to 0.5. But from -1 to -0.5 is equal to 0. From 0.5 to 1 is equal to 0. So the limit of integration here, I can modify it to be from -0.5 to 0.5 dt equal to 1 over 2. The integration of 1 is equal to t, and the limit -0.5 to 0.5. So it will equal 1/2, and make the substitution for t. The first value equal 0.5 minus second value -0.5. 0.5 minus be plus 0.5 make 1. 1 times 1 over 2 is equal 1 over 2. That's the DC component of the waveform. Means include DC component in it. All right. Second thing, I'm going to find AK and BK. The expression of AK and BK depends on omega. Omega naught equal to omega naught, okay, fundamental frequency. How can you find omega naught for this pulse or this waveform? You know the expression omega naught is equal to 2 pi over t. What is the value of t? 2 seconds. So it'll be equal to 2 pi over 2 seconds. It's equal to pi. So omega naught is equal to pi. Let's write down the expression for AK. AK is equal to 2 over t over the period t xt cosine k omega naught t the integration with respect to t, and k can take any value 1, 2, and so on till infinity. All right. Now, let's just modify this expression. First of all, the period t will agree from -1 to 1. And since it's only has value between -0.5 and 5, and the rest is equal 0, so the limit of integration will modify -0.5 to 0.5. I will say here, -0.5 to 0.5. The value of the signal, it's equal 1 between these two limits. So I will replace xt by 1. Cosine k omega naught t, we already found omega naught is equal pi. So I replace omega naught by pi. Let's replace by pi. Now I want to find the integration of cosine something. Oh, I forgot to make the t. T is equal to second here. So let's replace by 2. So what's 2 over 2? 1. Leave it as it is so you can remember. Now, equal to the integration of cosine. The integration of cosine is equal to sine. So it'll be sine k pi t divided by k pi. And the limit of integration minus 0.5, 0.5. Obviously, k pi do not depend on that time. So you can move it outside here. 1 over k pi. And just leave this one alone by itself. Now start substitute. It's equal to 1 over k pi. And you'll have sine. Substitute by 0.5 for the time t. Sine k pi, and t is equal half. Minus the other one, sine k pi time minus half. So minus half. Okay. Equal 1 over k pi sine k pi over 2. You have sine negative angle. We know that sine minus theta is equal minus sine theta. So this negative can go out. And you want to multiply negative by negative, be positive. So positive, so plus sine k pi over 2. When you add them, what you'll get? You get 2 sine. So you have 2 outside here. K pi sine k pi over 2. That will be the answer for this part. And when you do that, remember that k can take value 1, 2, 3 to infinity. Remember, that's ak. Let's see the possible values for this coefficient. When k is equal 1, you have a1, 2, substitute k equal 1 here, so you have only 2 over pi sine k is equal to 1 sine pi over 2. What's sine pi? No, sine pi over 2 is equal to 1, so the answer will be 2 over pi. If you use k equal 2, so a2 will be equal 2 over pi sine 2 pi over 2. So you cancel, so sine pi is equal 0. So it will be equal 0. If you go for k equal 3, just I'm trying to check if we have some formula here. A3, you have 2 over pi sine 3 pi over 2. 3 pi over 2 would make minus 1. So you have minus 2 over pi. So obviously it will be like, rotating between 2 pi, 0, to. So actually when k equal 2 and 4 and 6 when it's even, the value will be equal 0. So I can write this expression, ak equal to 2 over k pi sine k pi over 2, and now I can say I only have to substitute when k is equal 1, 3, 5, 7, up to infinity. So it's only working for odd numbers of k. All right. You finish AK, you go and find BK. BK, the expression for BK is equal to 2 over, it's the same as AK, but instead of writing cosine, you write sine. The integration over the period t, x of t, and sine k. Let me just check to make it fast. What we did here, oh yeah, sine k pi t. The same, just make it sine. dt. Again, the period is equal to minus 0.5 to 0.5, and t is equal to 2, and x of t is equal to 1. The same thing. It means I make integration of sine. Integration of sine give me minus cosine. So I will have minus cosine k by t over k by, you can take it outside with this constant, so minus 1 over k pi, and the limit from minus 0.5 to 0.5. So you have minus 1 over k pi. You substitute by half cosine pi k over 2 minus cosine minus pi k over 2. And you know that cosine minus theta, it's the same as cosine theta. So what you're supposed to do, you just can go ahead and just delete this negative sign. It doesn't make any difference with the cosine. Well, now if you subtract, they are the same, so they will cancel each other. So it'll be equal 0. What you get? You don't have BK. What does it mean? It means when you write the expression, let me write the expression for the general term that I showed in the beginning. We say that x of t is equal to a naught plus sigma from k1 to infinity, and then you have ak cosine k omega will be, omega is equal pi, so k pi t plus bk sine k pi t. That's the series. Now we found out is equal 0. Once it's equal 0, you have only, it'll be just simple, is equal a naught plus sigma k from 1 to infinity, and ak cosine k pi t. That will be the expression for x of t. Well, and we found ak. If you remember, that's the expression ak. ak is equal to 2 over k pi, all right, sine k pi over 2. So 2 over k pi sigma. And remember, is only the odd 1, 3, 5, and so on, up to infinity. 2 over k pi sine by k over 2. And we found a naught is equal 1/2 in the first step we did. So, we have to have t here, yeah. So when you do the expansion, just to give you a feeling, what does it mean? This it means the signal that it looks like a rectangular pulse stream. It's equal to 1/2 plus, if you put equal 1, you remember this term will be equal to, when you put 1 here for the k, we by t over 2. And this one, 2 over, put k equal 1, pi sine k equal 1, we pi t over 2. Take another one, just another one. You take not 2, 3. 3, so you have 2 over 3 pi sine 3 pi t over 2. I'm substituting by the value of k. And you can continue. Just, I mean, why I just did, I mean, like few terms. So this train of pulses has DC equal half. It means that like that, a battery equal half voltage. And then you have one fundamental sine pi t over 2. That's a sinusoidal wave. And you can tell what is the period of this one. You remember this omega is equal pi over 2. And the period, you can get it, is equal to pi over omega. And omega is equal pi over 2. Pi cancel pi, so it's equal 4, right? And that's, I mean, the one that you have. And then you have another sign. But the amplitude of the sign is equal to over pi. So we can say it's equal to over pi. And this another sign, and it's 2 over 3 pi. That's, I mean, it's smaller than this one. And the frequency is more because, I mean, if you can find that t is equal to pi over omega, and that's your omega here, 3 pi over 2, pi cancel pi, will be 4 over 3. That's the period, all right? So that's I'm trying to tell you, this pulse or this rectangular pulse train, now it consists of a battery, DC source, and some sinusoidal. So when you do your analysis, you can use each one separately, and you go ahead and finish your analysis. All right, I'm going to stop here, and next lecture will be also Fourier series trigonometric, but we'll take like a special case, what happened when it's even or odd symmetry. All right, see you soon.